All right, so today what we're going to do is we're going to be looking at drawing multiple bonds for covalent compounds. And this is more or less the same as what we did for single bonds or for the Lewis structures we looked at previously. We're just going to try to make sure here again that we have all of our valence electrons accounted for, the electrons are paired, and then the outer shell of the species are filled up where we obey the octet rule. So let's go ahead and start off by determining the number of valence electrons for O2. So each oxygen atom has 6 valence electrons. So this one has a total of 12 valence electrons. Okay, so let's go ahead and draw out the Lewis symbols for both of these. So we have one oxygen, so we have 1, 2, 3, 4, 5, 6 valence electrons. And then we have our other oxygen that also has 1, 2, 3, 4, 5, 6 valence electrons. Okay, so if we look at this, we can go ahead and have these two share these electrons here. Okay, so as we start to draw this Lewis structure out, what we'll see is that, okay, the octet rule is not obeyed for both of these. We've accounted for all the valence electrons, but we have not completed the octet rule, because if we were to take away this oxygen here while there's a single bond, we only have 7 electrons around this oxygen. And the same would be true for the oxygen on the right. So in order for both of these oxygens to obey the octet rule, they're actually going to have to share 2 sets of electrons. So what we'll end up getting is something that looks like this. And if we were to draw this out, we would represent those 2 pairs of electrons that are shared as a double bond. Okay, so as we look at this, so the electrons that are shared, remember for checking to see whether or not it obeys the octet rule, we take away the oxygen on the right and its lone pairs, not the electrons that are shared. So the oxygen on the left has 2, 4, 6, 8 valence electrons, so it obeys the octet rule. And then the oxygen on the right does the exact same thing. So this is a good Lewis structure here. Okay, so let's go ahead and consider nitrogen. So how many valence electrons does nitrogen have? Well, each nitrogen atom has 5 valence electrons, and there's 2 of them, so we have a total of 10 valence electrons. So let's go ahead and draw the Lewis symbols out for each of these nitrogen atoms. So we have 1, 2, 3, 4, 5 valence electrons on this nitrogen atom. And then we have 1, 2, 3, 4, 5 valence electrons on that nitrogen atom. So in a similar way, I would urge you to go through step by step like we did with the oxygen molecule. But what we can see is each nitrogen atom has 3 unpaired electrons. So the only way that these nitrogen atoms can obey the octet rule is if they share all 3 of those. And then what we'll end up having is something that looks like this. We'll have what we call a triple bond. So it's a higher order bond. And both of the nitrogen atoms obey the octet rule. We have no unpaired electrons. So we're in good shape. So this would be another good Lewis structure. So let's go ahead and consider what the effect having a multiple bond, a double or a triple bond compared to a single bond, has on a molecule. So we're going to look at both geometric and energetic properties. So let's go ahead and consider O2. So we just drew that Lewis structure previously. So So we had double bonded oxygens. And then for HOOH, we're going to learn how to draw this sooner than later. But this would be a molecular formula because it's telling you how they're going to be bonded to each other. Then we have nitrogen that's triple bonded. And then we have this species here. All right, so you can double check if you'd like, but all of these obey the octet rule. All the valence electrons are present, and all the outer shells are filled. So let's go ahead and look. Let's compare O2 and then HOOH, hydrogen peroxide. So as we compare these, notice that the oxygen-oxygen bond length, so that's what this bond length is here, it's an oxygen-oxygen bond length, that if you have a double bond or a higher order bond, the bond length is going to be getting shorter. And as the bond length is getting shorter, that bond strength is going to get higher. And the same thing is true for nitrogen. So again, note that N2 has a triple bond. So this is, again, shorter because it's a triple bond. And as that bond length gets shorter, the bond strength or the amount of energy that's required to break that nitrogen-nitrogen bond is increasing. So again, this is nitrogen-nitrogen bond, and this is the oxygen-oxygen bond. So you can see that, again, we aren't comparing apples to apples exactly, but in general, as you increase the order of the bond, as you go from a single bond to a double bond to a triple bond, bond lengths are going to decrease and the bond strengths are going to increase. All right. So next time we'll go ahead and start to consider a new method for drawing these Lewis structures, and it will be a little bit quicker, and hopefully you feel like you can draw molecules whenever there are a double or a triple bond present.